So welcome everybody at our unusual time for our Boston Action Club, but there's two reasons for doing so to have Aude Billard speak at noon. One reason is because Aude is in Switzerland and it is 6 p.m. in Switzerland, and I didn't want to ask her to speak at 11 shortly before midnight. The second reason is because we also have started a distinguished speaker series as part of the Institute for Experiential Robotics, which is a new institute at Northeastern, and Tashkin Padir is right here. So we double dipped because with your talk, we thought wonderfully fits both bills. So with that, we have this very wide, wonderfully wide audience. So thank you all for coming. I would like to repeat again my personal request to see as many faces as possible, because I would like to at least visually connect with who you are and where you are and make you participate in Aude's talk. So regarding participation, I would like to suggest the following mode, and that is, let's not use chat. I am totally terrible in getting sidetracked. I cannot do two things at once. I want to hear Aude, so a chat will not be attended to. The way of commenting and interacting, let's either raise a digital hand, or you can also, if there is a suitable moment, step in and ask Aude a question, which of course, given that we do have a hard time limit, we want to keep to a reasonable minimum and trade off lively interactions with keeping time. Okay, that now gets me to introduce Aude. Aude Billard is a professor at the EPFL, professor in robotics, and she has background in robotics and in physics, and has become a pioneer in the application of machine learning for robotic control and human-robot interactions. But while this is wonderful, the even more wonderful thing, at least from my perspective, is that she looks very hard into human movement domain and has recently even started to run motor control human experiments, which I find fascinating. So given those dual outlooks or these complementary outlooks, we weren't sure how to best represent Aude's research. And so we decided to kind of have two parts, which are definitely not separate as such. But the first part will focus more on her robotics work, and the second part more on the human work. And for the roboticists amongst you, don't just tune out of the human work. It's totally fascinating. It's manual dexterity in watchmaking. So stay tuned for the whole show. One more mention: Aude is highly recognized. She has received numerous awards from the IEEE Society, and she also currently holds leadership position on the executive committee on the IEEE Robotics and Automation Society. So with that, no more time wasted. Let's turn to Aude.
Thank you very much, Dagmar. Definitely a very good introduction. I'm blushing. Can you hear me well? Yes? Okay. I will share screen. It's a pleasure to be here virtually. Let me share screen and see if I can put it in presentation mode. Dagmar, can you please confirm that you can see it well?
Yes, looks great.
Yes, yes, okay, wonderful. Okay, so, all right. So the first part of the talk will be primarily on how to control robots and how we are moving step by step to try to get robots to have some of the dexterity that humans have. I'm particularly fascinated by this very fine dexterity that we have in the fingers and how we can manipulate objects in hand. I will just present a few of the work that we have done in that area. I have removed as much as possible all the theoretical materials, so I apologize in advance to all the roboticists in the room. I'll try to compensate by giving some verbal explanation of how we get the behavior that we see here. And I did that because I assume that the majority of the audience will not be in robotics. And then the second part of the talk will be more about studying how humans actually achieve this type of dexterity. Okay, so two things that are very interesting I find in these pictures, which are fake, not for the human, but for the robots. The robot cannot yet do that. But what I find fascinating in this is the fact that we really use all the degrees of freedom, multiple of them. If you look at what's happening in robotics, and it's still the case, unfortunately, in my lab to a large extent, that we can hold only one object at a time, and usually at the fingertip. But humans can do much more than that. They can have multiplicity of configuration and hold different objects within the fingers, and they really use the full number of degrees of freedom that exist in the hand. And we are still far from that in robotics. They also benefit, of course, from a wonderful sense, which is tactile sensing. And we are capable of doing that much faster than robots can do. So we're going step by step towards this. And the first thing that we looked at, and I wanted to present to you, is this part of the work. So in robotics, often, or for a very long time, people were trying to grasp the object around the center of mass to stabilize it, which makes sense. And it definitely does make sense because you maximize your chances to not drop the object. But if you look at the way that humans manipulate objects, it's not that frequent they actually hold it around the center of mass, because there are many reasons for not doing that. And these are a few examples of grasp that we do on a daily basis. Sorry. Typically the one, I hope you can see my mouse, the one in the middle here, where we hold this cup from the very top. It's not that stable, but there is a reason for that, is that one wants to keep the lids down and not have the content coming out. It happens quite frequently that we hold the object just at the very tip of the finger here when we want to hand it over to someone. It's polite. You don't want to touch the finger of the other person. And so these type of grasp are not that usual in robotics. And there is a lot of work in robotics these days to try to infer what you want to do with the objects, so the functional components of the grasp, in order to infer what will be the best grasp for the function. But it's still very open-ended, and we don't quite know how to model this function. So one thing that we looked at was simply from optimal control viewpoints in robotics, you can generate different optimal grasp depending on the objective function that you generate. So we decided to take an objective function that was quite simple. It was simply to minimize the torque, and then we put many different constraints. And we solve for kinematic constraints, for typically any conflict you could have with the object, any obstacle avoidance between the fingers, but also with the object. And we solved that with many different constraints and just this simple objective function, which was minimizing the torque. And the nice thing is that it gives you a non-convex optimization. And most roboticists will say, no, it's not nice, it's non-convex. So you have many different solutions. But actually it's nice because when you solve a non-convex optimization problem, you end up with many different solutions depending on how you start off the optimization. And so what we looked for was not the optimal solution, but was the set of feasible solutions. And so I'm showing you here a couple of examples of these feasible solutions that we found first in simulation. So what you have here is this robot, which we used for the simulation with this particular kinematic. It's a robot that has a human-like hand with 9 degrees of freedom. And we were sampling across all the possible solutions to our problem when the robot is tasked to only grasp a cylinder. Okay, without having the finger hitting each other. And you get all sorts of pose, and that's the funny thing. We got lots of them. And I'm showing you this pose, and I'm showing you just below that the equivalent pose in the human. But really understand that this is there is no intent in the way that we solve for this problem that gives to the robot the information that this is the particular pose that we're looking for, this particular motion. It was simply solving for it in an optimal control viewpoint. We actually got about 1,500 different poses, but when we looked at them, we could cluster them into subclusters, and we were about 14 different categories. Now, solving for that at runtime is very slow. We can solve that in a big computer, but it still takes at least a good second. And from a robotics viewpoint, and at least from my viewpoint, 1 second is slow, especially when you manipulate object, because you want to be able to manipulate that in milliseconds.
Can I just very quickly, you said 1,500 for your 9 degree of freedom actuator?
1,500 solutions.
Yeah, 1,500 solutions. So where and how is the cutoff for counting them as a solution?
Oh, that's when your solvers stabilize. So when it finds a feasible solution. So because it's a non-convex optimization, the solution that you will find may depend on the initial condition. So you can bootstart your solver at different configuration. So we sampled the initial joints, different configuration to start with, and then we solve.
Okay.
50. So even though you have 9 degrees of freedom, you end up with many different solutions. But in the end, these solutions are not that different. So what differs will be the position of the fingers on the object. Typically, that's what you see. And also the joint configuration of the fingers.
Sorry, what is the error function here? How are you deciding, what is the solver trying to optimize?
The solver is simply optimizing for the torque, minimization of torque.
At the hand?
At the fingers, yes.
Across the hand. Yeah.
So each of the finger will generate a torque to hold the object. Each of the joints, in fact, will generate a torque. And so we compute all the torques for all the joints. So we have 9 of them. And we minimize the overall torque that will be generated, or overall force, if you want, that will be applied on the object. Yeah. And then we have a set of constraints. And many of those constraints are nonlinear. This is why it makes it a non-convex problem. So some of the constraints will be, well, you have to satisfy the kinematic, the forward kinematics. So it needs to be a feasible grasp, kinematically speaking. You need to make sure that the fingers do not intersect with one another. And you want a finger not to intersect with the object either. They must be in contact, but not intersect. Yeah, okay. So, so because it was so slow, we often like in my group to balance machine learning and control. So to be able to do the retrieval faster, what we did was to take all these solutions. So we have now a wealth of solutions, about 1,500 of them. And then we can populate this into a machine learning algorithm. So what we did was simply to learn the distribution of feasible posture on the cylinder. So these postures are represented as the hand position with respect to the object. It's a relative frame of reference. The position and the orientation of the wrist, if you want, with respect to the object, and then the finger joints. We reduced that to 8 finger joints because 1 was not very useful. And then with this, we can generate, and this is of course just a visual representation. Here we have done just PCA and took the first 2 principal components for visualization, but the dimension is much higher than that. And from this, we learn a distribution. So for that, we used a Gaussian mixture model, which is a mixture of Gauss function. And what you see illustrated here is the manifold of feasible grasp. That means that within these regions that are highlighted here, every single posture is feasible according to the problem that we've set. And that means that there is a kinematically feasible solution, and it satisfies all the other constraints. And everything that is outside is an unfeasible grasp. But once you have this expression, the nice thing is that you can really solve and find a feasible grasp in milliseconds. So it's a bit win-win from both worlds. You have first used optimal control to find solution to a very complex problem. But then you store that once for all. It's a little bit like a human who will be searching first for a solution. And then once the human has found the solution, they will just store it in memory. So it allows us to store it in memory. And at runtime, if we start from a location which is far from the object, like I'm illustrating here, what you only need to do is a line search. And a line search is extremely fast. A line search on this probability density function, and as soon as you enter an area which is highlighted here, which is highly likely according to the likelihood of the PDF, then you're satisfied and you know that you have a feasible grasp on this object. And you see here typically the example that we can find in simulation. Now, everything was trained in simulation on a robot trying to grasp a cylinder. But what was really nice is that with these, what we call in robotics pre-shapes, it was sufficient to have all these solutions to be able to grasp many different objects. And we could show that we could really use this to hold objects in ways that are usually not seen. And so this one I really like particularly because you see the two fingers at the top are holding the object just in between the two phalanges and also applying forces to rebalance the grasp on both sides. Yeah, here are a couple of other examples also, which is typically carrying a wine glass or carrying a champagne glass, which is something that humans will do with the tip, with the thumb on top of the glass. And there are many different applications of this grasp. I show you just a couple of them. In fact, it's sufficient to have this pre-grasp to hold both a wine glass as well as a cell phone. You wouldn't think that it's the same grasp, but it's sufficient to do for both. Now, of course, when we do that for roboticists, it may be obvious that what we did not take into account was problem of stability. So it's implicit because we're computing for the torque, we're also computing for force closure and feasibility in this sense, but it's too sensitive to being exactly at the right posture. So this is an example. If you're not exactly on the object where you plan to be, then it will drop from the finger. So we decided to move this one step further and go back to our idea that, yes, we do have a manifold of feasible posture, but they were purely kinematically feasible. Can we now enlarge this representation to include also things that are stable from a force control viewpoint? And so for that, we needed to have a way of measuring what does it represent to be stable. And since we are not limited in the dimension, because we are using machine learning techniques that can handle relatively high dimension, then we decided to include tactile information. So we went through get this tactile information, we place ourselves in the frame of reference of the object here, and we generate now an estimate of how to control the object. So for that, we can estimate that we hold an object as if we had a sort of a spring and damping system. And so what we need to learn in this new manifold of feasible posture are both the joint posture, which is the kinematic, as well as now the control, the force control posture, which we translate as a stiffness coefficient at the fingertip, and the relative position of the fingertip to the virtual frame, which represents the center of mass. So we're basically learning the spring constant and the rest position of the spring. And we want to associate this to the tactile data. So we can gather all this at runtime. We can now train the system by showing examples, and this is one of them among the many that we could show. So we show to the robot, once you have chosen a posture, how can you now vary, by how much can you vary the position of the fingers on the object before you actually drop the object? You can use this and then learn this distribution. So it's a distribution of position, kinematic, as I said, and also this notion of stiffness and rest length. And then once we have that at runtime, when we get a perturbation, as we have here, then we can retrieve what will be the expected stiffness and what could also be the expected position of the finger, which is translated from the rest length and the distance to this virtual spring. And you can adapt, in fact, to perturbation. What you see here is that the robot refuses to adapt. It refuses to adapt to this last perturbation. So observe that it adapts to translation nicely, to translation that are horizontal. It refuses to adapt too much to translation that are vertical, and definitely refuses to adapt to rotation. That was done on purpose because we wanted the robots to remain stiff in certain directions. So we could teach to have directional stiffness, as we call it, such that it will be very compliant in translation, but very stiff in orientation. We then pushed that further and we trained it with many different examples with different mass distribution in different objects and different joint configuration. This way to show that the robot could generalize and could generalize also to change now the stiffness according to a change of weight. And the principle is always the same. You embed that into a representation of what is feasible in this kinematic and stiffness space. And then at time you can retrieve the desired stiffness or the desired position of the finger. So that allowed us also to do things that we like in robotics and are still difficult. Is this? It seems very simple, but being able to move the finger to restabilize at runtime is called regrasp, and it's difficult because you have to do it very, very fast. And so we can also generate this. In order to do that, if some roboticists are interested, I'll go in more details, because of course you need one thing further, is to be able to know where it's feasible to move the finger fast. And for that, we need to have a representation of the manifold of feasible posture onto the object, which one can also learn with another machine learning technique. And then we can project onto this manifold the solution in joint space. Recently, with a colleague at EPFL, Silvestro Michera, and actually also first with Levi Hargrove, we worked on getting this used for prosthesis. So you see here first work that we did with them to detect automatically a grasp from EMG data. And then we went with my colleague Silvestro Michera to see if we could combine our control system to stabilize the object in the hand, which you see on the left-hand side, and use this in combination with EMG control to enforce that the object will not drop when you have a wrong detection of EMG. So I'll play this just a little slower. What you have on the right-hand side, let me just stop it. On the right-hand side, you have a control system which is purely teleoperated, only detection of the EMG, which is noisy, but still fairly precise. This is the work done by these colleagues, so they can detect the EMG to close and open the grasp, but also to control each of the finger independently. The problem is that there are lots of noisy detections, so from time to time the fingers will reopen, and then we combine that with our stabilization controller that I've mentioned before. What we could show is that it's much more stable with a shared control. Yes?
So how many muscles, and how does it map onto the degrees of freedom of your hand?
Yeah. So first, we don't control the arm with the EMG muscle. The arm of the robot is controlled by simply tracking the motion of the arm of the person. For the hand, I believe that they're recording 9 muscles, but I must say it's not my part, so I will have to double check that. I believe that they're measuring 9 muscles for the forearm, the 9 muscles that control for the wrist and the hands, but I'm not totally sure there. And how do we map that to the robot? We don't have enough, so because our robot is 16 degrees of freedom, and so we don't have 16 to 16, we have 9 to 16. So we basically even reduced that, and we did a 9 to 5. So we're controlling each of the finger separately. So thumb, index. Actually, our robot has 4 fingers only, but we control 2 degrees of freedom for the thumb, so it's 5 total.
Okay, thank you.
And how do you decide on the grasp pressure, since that's so important to keep it from slipping out of your hand?
Yeah, so we have tactile sensors. I don't know if you can see them. They're covering the hand inside. And so as soon as we sense the pressure, we have ways in which we can rebalance the force and change the position of the finger to ensure that we have a stable grip. And this is done using, well, we have 2 different techniques. One is the one that I explained before, in the sense that we know what is feasible and when it slips and when it drops. So we will stiffen up when we feel that it's dropping. We may also change the position of the finger. It's not so visible. There are lots of other videos. I'm happy to send them to you to see how the finger can also change their position on the object to restabilize at runtime, based on a detection that the object is unstable. Yeah, so I don't know if this answers your question, or would you like something more precise?
Yes, thank you.
Carl has a
thanks.
question.
Yeah.
Thanks. I was wondering, I guess at some point the person might want to put the object down. So I was wondering how you disengage the stabilization.
Yeah. Yeah, it's not too happy about that for now. So we have two approaches. One is that we try to have a classifier that can detect also when you want to reopen, which then makes it one more class to classify for. Is the open and close, and also the motion of each of the fingers separately. The alternative is simply to use the non-class. So when you have a default class, which is I want to close the finger or each of them, and then when you don't pass the threshold in your confidence factor that you want to close, and you don't pass it for a certain period of time, then you decide that the person does not want to close the grip anymore and wants to reopen, and then you allow it to reopen. But this is a weakness of the approach, because on the one hand, you want to restabilize the object and you don't want to be sensitive to the false positives that are given by the EMG classifier. And on the other hand, you still want the person to be able to decide to reopen from time to time. So for now, to be quite frank, we don't have a very robust solution. There are the two solutions that I just mentioned. One is to retrain classifier to open, and then the other one is just to use the confidence on the classification for closing, and when you're below the confidence for some period of time, then you decide to reopen.
Reza has a question.
Yeah. How generalizable are these stabilizing algorithms to geometry and mass properties of the objects if the center of mass is way off from where you think it is?
As in any machine learning approach, if the data that you use to train is really too far from the data that you will use at testing, then you don't have a very good generalization. But we were surprised that we had a fair amount of generalization across different shapes that resemble each other, but typically different size of cylinders or different type of boxes that are square. Even things that were not necessarily perfectly cylindrical. So typically you have a lot of bottles that have this sort of hole in between, or this sort of shape, round shape, and that will still generalize fairly well. As for the distribution of the mass, we trained it with different distribution. Small, about 10-15% filled in, 50%, and then about 75%. And so you have covered a large range with this. So for everything that we tested that was outside this range, the controller was very successful. In fact, really, I mean, very, very surprisingly very successful. But I cannot claim that it will work for any material. One thing that is definitely extremely sensitive to is the change in friction coefficient. An object that would be extremely slippery, you may have difficulty to rebalance it if you haven't taken example of such. And to be quite frank, all the examples that we gave had a relatively high friction coefficient. Yep, okay, I'll continue. Dagmar, tell me how we are doing on time, if you want me to switch to the other part.
So we are at 12:30, so continue. If we get too close, I'll just let you know when maybe you want to prematurely switch to your human talk. But
Okay.
please keep going. It's totally good.
Sure. So now I'd like to move to the other part, which is it's a bit similar to what I said before, is that I really would like robots to be able to react extremely rapidly, more rapidly than they can. And so this is a large part of the work that we've done in my group, which I thought may interest some of you, because I know that Dagmar is working a lot with the chemical system. So this is this typical video that maybe some of you have seen. It was one of the first example of what we could do that we presented in general different places, is to be able to catch objects in flight, as you can see here. And so what's the challenge? I mean, the challenges are, of course, numerous. But we made it very difficult in the sense that we wanted to catch objects that are flying fast and that are not balls. In other words, that do not have 3 axes of symmetry, where you have to really orient yourself to catch it. And that's where it becomes difficult. And this is where robots become a little bit better than humans. So this is Lucia Pai. She was a very good PhD student in the lab. It's just that I'm as bad as she is, and most of us are bad at trying to catch an object like this. So unless you train yourself, it's very, very difficult to catch an object that is not a ball. And so the way that we approach this problem is I will describe it briefly here. So for the robotists in the room, you're very familiar with the fact that when you want to plan from A to B, then you have to solve, possibly also with optimal control, and you will compute a path, okay? And then it will eventually bring you there. And so when we just consider catching a ball, for instance, then we need to compute a path that will lead us to the ball, but we don't care so much about the orientation. So the only thing that we need to care about is which path do we follow. Is it a straight path, but straight in what? In Cartesian space, in joint space? And again, then as soon as you say that, you're already opening the box of, you know, what is the cost function? And there are an infinite number of paths and an infinite number of solutions. Okay, and it completely depends on where you start from. So the way that we deal with this is to say, look, what we like is not to have to solve it at runtime anymore. We want to do the same as what I described before, is that maybe you solve for the optimal path, optimal in terms of so many different things, you know, the kinematic feasibility, dynamic feasibility. It could also be all sorts of other things, avoiding obstacles, minimizing torque, etc. But once you have solved for that, you want to store a control function once for all that you can retrieve at real time. And the only way to store that is to have an actual explicit function for this. So analytical expression for this solution. And so the way that we do that is by using time invariant dynamical system. Here I write an equation, a simplified version of it, where we'll say, okay, we're going to control now for the motion of, for instance, the end effector, as I illustrate here, but it can be done also for joint control, and you'll see examples of this with human-age robot in a second. But we control for that in velocity space. So we say, okay, let's have a velocity flow, and it's unique and it's described uniquely by this function f of x. And if I do have that, and if I have a number of properties associated to this function of x, then I have a closed loop control system that I can rely on thanks to the property that I have. And so now another question is, what happens if the object moves? Can I reuse this flow? And so what we wanted is to be able, of course, to reuse it, especially because we wanted to catch things flying. So clearly the thing moves, and clearly you have to adapt to the motion all the time. So a little trick is simply you place your frame of reference on the object, the origin on this object, not just the origin, you can put also the entire frame of reference aligned to the object, which is something we do to keep the orientation going. And then when you do that, then each time that the object moves, and if it, you know, and that's your attractor, that's where you want to get, that's your stable point, then all what happens is simply that you incur a perturbation in this flow. But this flow has an infinite number of solutions, and all of them, you're sure that it lands you at the object. So we construct a function f of x, which we know are to be asymptotically stable at the origin of the system, and the origin is on the object that we want to track. And the question is, what is f? So to get f, we can either train a robot, typically by human demonstration. This is an example. You could train, move the robot, and show different example. Or those days, we do it with optimal control. So we solve, as I explained before, with kinematic feasibility and all sorts of other constraints. Once we have that, then we can learn a function. And we want to learn this function and ensure it's stable. So of course, in machine learning, you can use all sorts of machine learning techniques to learn this function, but none of them by construction are stable. Here are just example illustration of if you learn this with support vector regression or neural networks, then you'll have a very accurate representation of the dynamics. So they're very accurate of expression for f of x, but you will not be sure to stop at the target. And it's catastrophic if you don't stop, because you may just generate a motion on the object as you catch it and then let it fly somewhere else. So we revisited this machine learning technique. We've been doing that for years now. we just go back to the optimization problem of the machine learning technique, and then we impose control constraints. So the first control constraint is the one that I mentioned before. You want to converge to a fixed point. Typically, you want the point, the origin of your system to be stable, and you want the system to be asymptotically stable like this. So there are different ways in which we can solve that, but when the function is nonlinear, a lot of people use Lyapunov stability. More recently, we've started using also contraction theory, working with Jean-Jacques Lotin. But I'll present here the simplest version, which is Lyapunov stable. And so the problem is what is f and then what is v, because we have neither the Lyapunov constraints nor the function f. So we've shown different ways in which we can learn either f or v or both of them. I'll present to you only one example where we fix v. So we have examples of trajectories. Okay, we want to learn now a function. What we can do is again use, for instance, a probabilistic model, which is a distribution of velocity and position. Okay, I'll go a little quicker here. When you want to query for the velocity, you have a closed form solution. In fact, for all machine learning techniques, when you query for the expected position or expected velocity, you get a closed form solution. So that's nice. That's the form that we're looking for. But it's parameterized, and the parameters are usually learned by maximum likelihood or convex optimization, etc. So we revisited that, and then we applied a different function. Here, the Lyapunov function was simply quadratic, and then we derived constraints explicitly on the parameters of the machine learning algorithm. That will enforce stability at the target, and that will also enforce that the energy decreases such that your system is stable. That was the very first work that we did, and then we had lots of other things that are extension of that. I won't go there. I'm happy to send paper. And so that gives us this nice functional. You have it in closed form, and then you can do many things with it. So this is the simplest that you could imagine, is simply to go to the object and stabilize at that object, as you see here. Observe that the hand is really moving with the object, because the object is the origin of the system. So each time that the object is perturbed, then basically it's the same as if you're perturbing your hand. So that it makes a bit this funny motion where the hand is adapting and basically moving with the object as if it's tracking or as if is controlled implicitly by the object, which is the case. We can also do this with multiple attractors. So if you want to catch an object which has a shape which is complex, like this one, then you need to have different grip. And this is a combination between what I presented at the beginning and this control system, that you may want to close on the object with different joint configuration, but you want to switch across those at runtime very fast. So we took on learning not just one functional, but to learn a combination of those functional. The machine learning technique, this is same as learning a partitioning of the function. Then you want a partitioning such that one partition is stable at one particular attractor in joint space. Here you see it in 2D, but think of it as one grasp. And then another partition will send you onto another grasp. And if you, instead of having 3 of those functions, you have one single function, then you can retrieve at runtime a control system that switches across these different grasps. I don't think I want to go into details unless someone is really interested. So maybe I'll just skip that real quick. But if you can.
One other question. Will the robot attempt to catch an object which is impossible to catch, like if it's too large or outside the range of reach?
No. Short answer, no. Let me get there in a few slides. No, because we compute the workspace. We have also an explicit expression for the workspace. And so we're going to choose only the points. First, we're going to go only when the object is reachable. So we'll travel the workspace, and then we'll have to choose the point that is the most likely to be caught within the workspace. Okay, so I'm happy to come back to how we derive this, but in the end, we have a closed form solution for that, and we can catch different objects. This does not answer the question that was just asked. Here you have just an example where we switch across 2 grasping points, the neck and the bottom of the bottle, and we can switch across those at runtime. And here it's extremely fast, and you have about 0.2 seconds to catch the object before it falls. And so you really have to switch across those without planning. So, and for the complex object, which is which is even more of a challenge. This is the one that I showed as a teaser first. In order to do that, we need one more ingredient, which is to be able to predict ahead of time. And this is answers the earlier question, because in order for me to decide how to catch the object is not just to decide where I catch it, with this big or small grasp, but it's also where in space. And as I need to travel there very fast, I better have a good estimate of where it's going to land within my workspace. So to be able to do that, you need first to have a good estimate of how the object travels in space. And it's not so trivial, especially when the object, the points that you want to grasp is not at center of mass. Because when it's not at the center of mass, then the trajectory does its illustration here, but it's typically what happens is that the object looks as if it's going towards you and then going back and then towards you and then going back. So it's really not a ballistic motion. So in order to get an estimate of that, we used again machine learning. So we threw these different objects in space. We tracked very accurately the position of the handle in this case, or the point that we wanted to grasp, with cameras that you see on the roof that can track at about 240 hertz. And then we learned a model of the, and I write here the equation, the x dot dot, in fact, represents, for us, it represented the translational acceleration as well as the rotation. And so we need to be able to account for both the translation and the rotation of the point that we want to grasp at. And once we have a closed form expression for this, which you can get from so many different things, in this case, we compared support vector regression with neural networks and all of the others. And SVR was the best because it gave us a very crisp and precise function. Then we can use it and compute a derivative and put it in an extended Kalman-Fiedler. So now we have, yep, sure.
Yeah, that's totally fascinating, especially when I'm thinking of humans, where one assumption is that we know the dynamics of the flying object in its and configuration, and thereby predict the whole show. Whereas you show also what I understand as an adaptation to the relative motion between the hand and the object, or with that reference system in the flying object. So first easy question is, have you compared the hand trajectories to human trajectories? To what degree that these different, call it elements in your algorithms, are also present in the human catch, or vice versa, look at humans to maybe gain some more ideas for your robot hand catch?
So we were inspired by the human to some extent, because humans are in general not capable of catching that. So did we compare? We often use the human as a way to train the original dynamical system for the trajectory in space. But what we used the human for was to understand how human control for the closure of the finger in synchrony with the hand motion. Because that's absolutely key. If you want to catch the object in flight, you need to close your finger real quick. I mean, really on the spot. And if you start closing the finger too early, then chances are that your finger will hit the object before you actually have it in the palm, and it will bounce off. And if you're too slow, then the object will bounce also, and you will not have the time to catch it. And so we actually had humans come in the lab we had them wear motion sensors for the entire body, including the hand, and had them catch balls, which they're good at, not rackets, balls. And it appears that there is really a coordination pattern between the closure of the finger and the reaching movement, which is known, but we were particularly interested in really the actual parameter. What is the aperture of the hand and the closure, the speed at which both synchronize? So we were looking at the coefficient of synchronization between the arm motion and the closure of the grip. And we actually took the human data for a robot controller as coordination patterns. And that was very good. It was very helpful. I guess we could also have estimated it in simulation to see what would be the best solution. In this case, we took the human as a good example.
Thank you.
Yeah, so once we have this dynamical system to reach an object, and we have an estimation of the object's motion, what happens in real life is that as the object flies, we always have to adapt our estimate of where the object will land, because we get real measurement and there is a discrepancy. So we need to adapt to that, and we can luckily adapt to that, because as soon as we change the position where we want to grasp the object, then to us it's simply a change of the origin of the system, and we eventually get there. And that answers the earlier question: is how do we choose this position, where to grab the object? And so the way that we did it was to have a representation of the workspace of the robot. So the workspace of the robot is here, the position and the orientation of the hands. The orientation is absolutely key, because you need to orient yourself with the orientation of the racket, for instance. So this is a high dimensional workspace, and we use same thing as what I presented for the finger earlier on. We learned a probability distribution function of all these posture. So we learned the feasible space of posture in position orientation. And the region that are the densest, which correspond to the darkest here, correspond to the region where you have the highest number of feasible posture. And we decided that this densest region were those where we were the most unlikely to fail grasping the object. Let me explain why. The object flies, okay, and you have an estimate, but it's still not so precise. So when it starts entering your workspace, chances are that as it travels your workspace, the object will be slightly off what you expected it to be, maybe 2-3 degrees off compared to your estimate. 2-3 degrees off is fairly challenging when you want to catch in flight. So you need to be able to adapt and to at runtime immediately orient the hands to align to this new estimate as you go. So we estimate really fast because we have this tracking which goes at 240 Hertz, but still the robot is slow. So you need to be able to adapt. And what if suddenly now you have to rotate by 2 degrees and you're at the edge of your joint space? Then you cannot rotate anymore. So the region that are densest in terms of configuration space are those where you have most chances to be able to reorient at runtime in millisecond to get the right orientation and the right posture to grasp. So this is how we chose D point. And yes, we don't get the robot to start running when we see that the object is going to fly outside the workspace. And by the way, this happens very often because as a human, it's not so easy to throw the object at the robot correctly that it reaches the workspace. We had to train humans to throw correctly. And so yeah, these are just a couple of videos where you can see the adaptation, especially when slow down, you can really see how you have to orient the hand just at the last minute. It's also a little more obvious for object like this one. Here we have a different hand which is a little more robust, and that needs to adapt to different orientation. So here you can really see that you have a need to predict where the object is going to land, and you have a need to orient and change the posture of the hand and close the grip simultaneously. And you cannot have a fixed timing for closing the grip because it totally depends on the duration of the flight. And this will depend on where you decide to catch the object. And since you change your estimate of where to catch the object all the time, then you have to change also your estimate of when you grip it. Well, okay, we also extended that to be able to reach more complex objects, such as a flying bar here in synchrony. This work, I won't go into detail, but here was really exploiting this notion of coupled dynamical systems. So we could couple the two arms so that they will reach simultaneously. This concept is completely borrowed from human motor control. It's the famous concept that if you reach with your two arms, which I cannot show to you, but if you want to catch with your two arms, there is one slowing down and the other one accelerating so that you reach a point at the same time. And this coupling seems to be innate from what I understand. And so we put the exact same principle. We put a coupling into these two robots such that they will reach their respective origins, so the respective targets, in synchrony by coupling, in fact, the two equations. And so it's quite nice because you see them, they do a completely different trip. I mean, sometimes one will go down, the other one will go up. It totally depends on how the object is flying, but they will get there at the same time. Okay, I don't have any equation here to explain that, but we also extended the system to be able to control for force and to adapt. And this is this adaptation for control for being able to hold stiffly objects and still being compliant and at the same time flexible and be able to adapt to the orientation and position. So for now, we just have two robots holding an object stiffly, but you can break the grip and get them to go back to the object in synchrony. So you have the synchronization, but the synchronization here is not just in kinematic, but it's also in force. You see that you can move the object and they can reorient, and they reorient simultaneously to go and grasp the object and grasp it with the right amount of force. And so we've also extended that for controlling a robot, which is humanoid, so to control for balancing as well as holding an object, and to control also for perturbation. And I'll just go a little quicker. And then we can combine one further thing between controlling the dynamics, the navigation of the system, and the grasping.
There's a question from Rashida.
Sure.
Hi, Professor Billard. So in the catching task, how did performance change as a function of coupling, and could coupling change in real time?
I could hear you very poorly, unfortunately. Could you please repeat? There was a bit of noise. Hello?
I repeat Rashida's question. She was asking whether how the catching changed as a function of the coupling, if you changed or looked at different couplings, and whether that coupling or coupling strength changed during a single catch. I guess this was Rashida's question.
Dagmar?
Yeah, could you hear me?
I lost sound for a little while. I think the problem is on my side. I'm sorry, can you repeat?
Rashida, why don't you go ahead?
Yeah, Professor Billard, I was wondering if performance changed as a function of coupling, and if coupling parameters could be adjusted in real time.
So the performance for the catching is completely dependent on having the right coupling. That's absolutely clear. And if the coupling can be changed at runtime, it could. We haven't done it, but you could do it certainly. But then the question is, how do you change it? So how do you change the coupling? If you want to prove that your system will be globally stable, so that both of the arm will reach the same point as you're changing the coupling, then you will have to have some constraints on how you're changing the coupling function. The change must be such that the speed at which you change the coupling is slower than the speed at which the two systems need to converge.
Just an idea. I mean, there's a limit to what degree the human hands want to do very different things. So you could have a symmetry constraint or antisymmetric symmetry, so that, yeah. Did you hear me?
Yeah, I could hear you. So you mean one could add other constraints to decide how to move?
Yeah, I was just thinking that your two robot arms performed very different movements, which of course on the one hand is a very nice demonstration, but I think the human hands have limitations in how different they can move. So that could be an addition to potentially change or change the coordination between the two hands.
Yes, I mean, certainly one could add other constraints to adapt the coordination if need be. One thing also that we looked at was when you want the robot to grasp things and the two arms have to cross their relative workspace, you don't want them to hit each other. So you also want to travel in a workspace that keeps changing. So it's a deformable workspace. And so as the two arms come close to one another, the workspace of the right arm becomes reduced. And as the left arm moves away, then suddenly the workspace of the right arm becomes larger. So that's also possible to model that. Because when you model the dynamical system, you can also model a region in which the dynamical system is valid and can travel in space. And you can model this region as a shrinking region that grows and decreases. So this is also, these are a few things that we've looked at, but mostly in Cartesian space, not in joint space, which is a more complex problem.
So just another organizational issue. We have about 1 o'clock. So maybe it's about time to transition to your second part.
Yes, sure.
Can I ask one last question before you transition? Does your catching algorithm use a model of the gravitational field, or is it based solely on the path of the object?
Yeah, it's not there. It's implicitly there. So when you write the equation, it's such a simple, when you simply write this, you say the acceleration depends on the position and the velocity. You've just written Newton. And so you're not saying anything else. And so this is learned implicitly in the parameter of the model. So we could have written gravity, certainly, but that would mean that we know the mass of the object, which we did not want to know in advance. It's particularly the case when we throw the bottle, which is half filled. Yes, we could measure what's the filling, but the interesting part when we are throwing an object which has some liquid in it is that as the object travels, the liquid travels. So the mass is not constant. The distribution of mass is not constant. The mass is constant, but not the distribution of mass, not the matrix of inertia. So what is nice is that you can learn. You can learn how, as the object travels and rotates in flight, how its dynamics will change. And this is due to so many different aspects. Some of them are the change in mass and mass distribution. So the gravity plays a role, certainly, but also in conjunction with the distribution of the mass. And another aspects which are more complex to model are the friction, which is quite difficult on a racket, for instance, to model a friction because the racket is very unhomogeneous. Yeah, and air drag and things like that.
Okay, thank you.
And maybe if you do transition to your next part, let's just open for any other more general questions to this part.
I had one question. Since Dagmar offered, I would have waited till the end. I was wondering that you sometimes have like 3 fingers. Of course, you need the thumb, but 2 digits here or 3 digits or 5 digits. Is it just determined upon the task, or does it give some computational ease if I have less fingers? Or like, how does adding these 2 fingers help me or create problems for me? Or even more than 5 fingers? How does that work in this robotics world?
So the how can I answer that briefly? In robotics these days, you don't have at your disposal so many possible hands, unfortunately. So first of all, if you don't develop hardware yourself, you have to buy hardware that exists. And majority of people still use grippers, which are really 2-finger, because it's handy and there are many different reasons. And you can already do quite a lot with just 2 fingers. 3 fingers, just having 3 is less important than knowing whether you can control them independently. And so there are very funny configurations. Sometimes you have 3 fingers, but you can move those 2. I don't know if you can see me. So yeah. You can move these 2 and enlarge them, and then having to rotate, which I cannot do with my hands, so that at some point, they are really all equidistant. Like maybe they have exactly the same distance between those, and that's very handy, typically for symmetrical objects that you want to hold. And if you couple that also with a 360-degree motor here, then you can rotate and you can put in a bulb in a much faster manner than you could as a human. But it works only for certain objects. And there is a huge trend of people trying to have anthropomorphic hands, not necessarily for a good reason, I mean, when you want to have a prosthesis, clearly there is a reason for doing that, because I mean, it would be bizarre to have a sort of a gripper instead of a hand. But other than that, I think it's just that roboticists are somehow fascinated by the human hand. But it doesn't make so much sense because the hand is asymmetric. And so I don't find this design particularly good, I must say, because often it forces you to reorient the hand of a robot. And then it creates another problem in terms of planning, because you have to find the right orientation, and you basically make your task more complex than it would have been if everything was symmetric. So I'm dreaming of having hands, first of all, where we could grasp this way, but you could completely rotate it, which I cannot do with my human hand. But in robotics, you could do that. You know, you could just swap it. That would be so much easier. Short, it's a long answer here too, but at some point, we started drawing funny hands that one could create, and we hope that someone will work on this design at some point.
Thank you.
We have more questions on this first part.
I have a sort of simple question. Have you looked at all about juggling stuff? Because what you're describing is basically, I mean, you have juggling balls like these, and you have juggling clubs like these, and what you're describing is basically those two things. So I'm wondering if you've looked at any of that kind of stuff.
Juggling has been looked at in robotics, not my group in particular, which is interesting. And you know, when you juggle, or whenever the robot sends the object and catch it, it's in a way easier. It's easier. That's why jugglers learn it, and they can juggle themselves, but not juggle when someone else sends you the thing. Because
they definitely can. They train. That's like the thing you're talking about, like of passing is kind of.
But they train themselves, no? Both of them.
They train together, yeah.
Yeah, that's the thing. The thing is that we wanted the robot to be able to catch it from someone random, never seen, that throws the thing at you. That's more complex because yes, we do have a prediction of how the object travels, but you don't know how the person has throw it at you. Right. So in that sense, it creates more uncertainty. So it makes the task a little more complex for a different reason, because of the uncertainty. But the juggling is very complex, especially when you start to have many of them, and I'm sure you're an expert. So.
Yeah, I guess if it's repetitive, then you get the sort of the statistics of the repetition versus the one-off where you just sort of have to figure it out from scratch.
Yeah. And I guess you can predict, especially when you throw, or when someone, and it's always your partner throwing it. It's like people throwing knife at each other. I mean, if you do it with someone you've never seen, chances that an accident arises is probably fairly high. But aside from that, the humans are incredible at learning this. In comparison, robots, if you were to compare, robots seems to be fast at learning, but in reality, when you look at the number of examples and the time, if you were to scale computer time into human time, they're slow. Huh? So I think we still have lots to learn from how humans manage to learn that. Yeah. Cool. But if you're interested, I can point you to, there have been quite a lot of work looking at juggling in robotics.
Yeah,
in simulation.
I'll contact you after. Yeah, thank you.
Yeah, sure.
Okay, maybe let's move on.
It's maybe a bit too much, don't you think, Dagmar? Because
we'll keep going. I know that there is a few very, very, how shall I say, people with stamina. I know that. So continue. And we may lose people who have more things to do, but I would say let's go according to plan. Move to your second part.
Sure. Okay. Can you see the slides?
Yep.
All right. So really, this is a work that we started just about 2 years ago. So it's really very preliminary. We just have a few results. We've been collaborating with Dagmar recently on helping us to analyze that. Oops. And so here is an example. Oops, just stop the sound on my side. Oops. So what we've been looking at was to try to understand how humans acquire this dexterity and why they are so good at doing it. And one thing that I particularly wanted to understand is how humans manage when they're doing a skill such as watchmaking, it's a typical Swiss skill. How do they manage to go over the sensory motor noise and be able to sense so precisely the forces and also know how to configure their two hands with respect to one another? Because it's a lot of degrees of freedom to configure with respect to an object in order to manipulate the object, and the object is often moving. And so, but they do acquire that. So so there was an attempt to try to understand how people acquire that. And so here is a video of a typical watchmaking that we're looking at. So you have a watch face, and you have what we're looking is a specific subtask of watchmaking, which is simply to unscrew something which is called a plate, and then under that to remove the spring and then put the spring. So I'll come back with another example. We just, for the first part of this analysis, we focused on the spring element. So the spring element, you see it here in the watch. It's this tiny blue element here that you need to insert, and it's absolutely crucial to the functioning of the watch. Okay, this is a CAD drawing that we reconstructed, and you need to do that using two tools. One is a tweezer, and the other one is a wooden stick. And you need to place it, and both hands have to work in coordination, because that's the only way that you can insert it. One needs to hold the spring, and the other one needs to push in so that it will just insert at the right place. So there are really two steps, and the first is to be able to position the spring and apply just the right amount of force, and then in the right direction to be able to insert it and fall into the step. Now it may look simple, but actually it's very, very difficult. As you can see here, it jumps all the time. So when we follow apprentice doing that, we see more failure than successes, really, and it's very annoying for these apprentices, because they try to put it in, and you see it jumps all over the place, and it's so small that it's difficult to see and to find, get back, etc. So we followed apprentice over the course of the study. In fact, the study lasts for 4 years, but the most important years for this type of manual skills are the first 2 years, and especially the first year. So we followed a cohort of 23 apprentices, and we had 4 experts who are the teacher, are very skilled at doing that. And we had them repeat the same task over and over again, and we recorded what they did. In order to be able to record that in a way that we could model it, we put a lot of sensors on them, as you can see. So the first thing that we did was to put on the watch face a force torque sensor, and then we also monitored the hand. So on the screwdriver, the tweezer, and the stick, we needed to be able to monitor both the kinematic of this object as well as the kinematic of the hand. So we have sensors, as you can see, on the fingers, which measure pressure. We have a 6D, so that means we can measure force and torque sensor on the watch base that measure the force applied by and the torque applied by the person onto the watch. And then we also record the position of the finger with a motion capture system by using markers. So these little dots are recorded by camera, and we have 8 of those GoPro cameras that are highly accurate. And then we can reconstruct the position of the fingers, as you can see here. This is overlaid now on a video. So after having done a recording, we can reconstruct the position of the finger, and then from there we can reconstruct the kinematic of the hand. So we have the kinematic, the movement of the hand, we have the pressure of the finger, and we have also the pressure applied on the force applied on the watch, and we have the motion of the instrument also, and we also have tactile information on the instrument. Now I'll focus on the result of the first part of the analysis. So the first thing that we wanted to understand is what do they learn when they're placing this spring, because it's so, it's complex. They have to learn how to position the hands, but they also have to learn the task, and they have to do it at once. It may seem simple to you, but for me, I thought there was really a lot to learn at the same time. And there is not so much verbal teaching from the teacher. In fact, the only thing that happens is the teacher shows, once or twice how to do the task, and then the students are left to repeat and repeat and repeat over and over again until they achieve it. So let's contrast a typical beginner. Okay, so this is a beginner trying to insert this. Right, I'll let you watch a little bit the video. And this is an expert. And so if I were in the room with you, I'd like to ask you, what do you see a difference? Do you see a main difference between the two? Yeah, since we're interactive, I don't know. So one thing, if I replay it, one thing that you may observe is that here the beginner keeps shifting, keep rotating the watch all the time. And in fact, many beginners do that. They turn it around, they turn it again, they pick up, then they turn it again, but not always putting it in the same position. They just do all sort of orientation of the watch. And if you look at the expert starts from some location of the watch, and then poof, poof, to motion, does not touch the watch anymore, and then place the spring. And we have several examples of this. So clearly, the expert has a model of what is the correct configuration of the watch relative to the hand, and the beginner is learning that jointly with learning how to apply the right force, how to position the hands on this. So all these degrees of freedom need to be learned, and they need to make sense at some point in the brain. So we try to model this more precisely. What do they learn? What is the correct orientation of the watch that leads to success? So recall that we have the spring assembly. So we need to apply force on the spring to insert it. And that's crucial, because if you apply the wrong force in the wrong direction, then poof, it jumps and gets out. Okay, so clearly the orientation of the hand with respect to the watch and the force that you're applying, which needs to be also aligned with the position in which you're applying, in which you're holding the spring, needs to make sense with respect to what is feasible and what isn't. So we divided the watch face into 8 different regions that you see here, and then we looked at the distribution of region, if you want, that are used by the novice when they're trying to insert. In blue, you see the distribution of region that they're trying out. You see that it's widely distributed. There are only 2 that they're not even trying, because this is orthogonal to the actual position. So clearly that they know it's to be ruled out. But the others region that you have in the middle, they may look feasible, but they are not trying them. And if you look at the expert group has a little bit of variability, but it's always in the same region. And in fact, this region makes total sense, because that's the only one that can lead to success. In fact, if you take it the other way around, first, it's very uncomfortable, and second, most of the cases, you lift the spring so it gets out of the hold. But again, nothing is explained to the student. They have to discover that. So in order to understand this one step better, and also come closer to something that we know how to model, then we want to see, can we model what this problem is from an optimal control viewpoint. So the first thing we did was clearly to have the kinematic of the system, so to have the kinematic of the hand. So that, as I said before, we can track the position of the finger, and then we can reconstruct the joint position. We also have the kinematic of the body, of the upper torso, the elbow and the wrist. And then we can start to try to model what the task is about. One thing that we wanted to model is first the manipulability. How do I place my hands? The manipulability is made a little simpler than if we were to control for the entire body, because the watchmaker have to put the elbow down on the table. So it reduces a little bit the number of degrees of freedom. So we focused essentially into the orientation that they will have for the 2 arms, and how this orientation will also generate a directionality in terms of the force that they can apply and stay under motion. And so from there, we can compute what are known as force ellipsoids, which is a representation of the distribution of force that I can generate. And there are some orientation that does not allow you to generate forces in all possible directions. So the more elongated the force ellipsoid, the less freedom you have in the directionality of the force that you can apply. but often also the more elongated it is, the more chances you have to be able to apply more or less force, and so to be able to scale the amplitude of the force. So one can model that, and then we could use indices that exist in the literature to be able to measure what people may be optimizing for. So the first thing we looked at is so-called a task compatibility metric. It's something that will look at whether you orient your hand, so you orient your ellipsoids in force, but also in motion, with the requirement for the task, and how well are you aligned with this. So this is a complex graph, and I'll just forget about everything and just look at U, which is the direction of control. This is the direction of the force, and you want this U to be aligned. This is the desire, the one that you need in order to insert the spring, and you need this to be as much as possible aligned with the Jacobian of the of your arm, of your endpoint here in this case. So I will not show all the results, but what we could show with such a modeling is that the expert subjects align better with this direction, the U, with also the optimal force transmission direction. In other words, their force ellipsoid is best aligned with the direction of U for the dominant arm, which for all our subjects was the right arm, than for the novice. I mean, that's quite obvious. That's how they are successful, but one can quantify it. And then we wanted to model how we can generate this posture. So we took this task compatibility metric. We added to that the manipulability, which is a usual one, which measures simply by how much can I move my hand around once I've chosen a particular posture. How can I reorient? And then join this comfort as one other metric. And as a first attempt to try to understand how the subjects learn these two different aspects. One is to understand what the task is about. So basically is to infer what the U, the desired, the optimal U is. And then how do they use their estimate of the U to generate the best posture. So one approach to do that is to do this with a bi-level optimization. So bi-level means that you optimize the first thing, then you use your optimum for this, and then you optimize the second thing, and then you go back. So you can optimize your estimate of what the task is about, which is the first metric here. So it's a balancing between all different costs and your task compatibility. And then once you have this, then you can try to find the best posture and conversely. So you can change, you generate a new configure, you generate a new cost, a new estimate of what the task is about, so your new objective function, and then from there you generate a new configuration, and then you go back and forth until you stabilize. So if we contrast that this is a model, so it doesn't mean that this is what they're doing, but what the model will tell you based on the data is that apparently the novices give less importance according to this way of estimating the objective function. They give less importance to doing well the task or this task compatibility than they do to other things. I'm sorry, that's the exact opposite. The experts look as if they give less importance to task compatibility than they do to join discomfort and to the manipulability.
And joint discomfort is a verbal report.
No, it's measured from this, from how far they are from the limit of their joints.
I see. Okay.
Simply, and we scale that by the motion range. So we just go with what we call rest position. So rest position will be the middle of the range, and then we normalize by the range. Okay. So we're looking at the variance from the rest position, if you want, normalized variance. But then, so it will seem as if it's bizarrely that the experts do not care about being compatible with the task, but no, it's not this. Is that the experts have already found what are the region in which they need to align with the watch. And so in fact, they're at the stage where task compatibility is less important to them. And what matters is that at that stage, they can pay more attention to joint discomfort and manipulability. And so that you can also find when you're looking just at the metric of task compatibility. And what you find is what is expected, what I said just before, is that the expert group the index for measuring task compatibility. So how aligned are you with the direction that you need to align to? Then experts, of course, are better aligned with their good arm, the right arm, the dominant one, than the novice one. So they have this alignment, and basically when they're doing this optimization, when they're improving over the trial, what we are modeling, and then they seem to be improving only for joint discomfort and manipulability. So the variance that we see in them reorienting slightly their hands with respect to this direction of the task seems to be an effort of being more comfortable or having more manipulability, but they've already ruled out all the other positions. And I don't know, I mean, we're already out of time, so maybe I should stop here.
So
sorry, it's too long.
To the time because it's daytime and people have other things on their agenda.
Yes.
I would love to see more, but maybe we'll close here and open for more questions.
I had one question. These three cost functions, do they have a common solution which optimizes all three, or there's a trade-off? Like I can see that the experts first figure out the compatibility thing, and then they don't need to care for. But if you try to estimate mathematically, do you get can you get a unique solution which minimizes everything, or that's not possible? You just have to learn one, and then you learn the other, and then you learn the other.
Yeah, there is not a single optimum. No.
And
so indeed, then you have a sort of a. But is it, to be quite frank, we haven't counted how many local or how many optima you could have. But there are different that are balancing the cost. Huh? So the different region that the subject choose, they're really a balancing between the two costs. So it would be nice to plot the absolute value of the objective function, but clearly one of them is usually less comfortable. So you will reduce, your cost on comfort, but then you will better align with the task. So no, there isn't quite an optimal. But I like your question, because in fact we should look at it, because it's possible that this variability is simply also from them not having an accurate estimate of where the optimum is. So yes, we should revisit this. To be quite frank, we haven't done that. So.
And whether if that gives light on which one they should, like it looks like all experts learn to do the compatibility first. It's better to get the angles right first rather than care for other costs. Am I understanding that right? Like.
Yes, but the thing is that they don't know what the task is about. So I hear you, huh? So that you will think they will just try most uncomfortable posture until they get it right. They don't seem to be doing that. They still seem to care about comfort. Probably because they do that for hours. It's very repetitive, so it's probably tiring, I guess. Yeah.
Thank you.
First, I wanted to make a comment that nowadays you should move from watches to iPhone repair, because it's the same kind of thing, this fine, delicate movements. But my question was, why are the ellipsoids, the right and left hand ellipsoids, so different?
Maybe it was just my visualization the representation. They shouldn't be different. Okay, sorry. They are different in the sense that we assume that the right arm has potentially more strength, so can generate more force.
But strength is not an important variable here. Each arm has more than adequate strength to do the task.
That's true. So we should not have taken that, and we should have scaled it by the amount of force that was generated, and we looked at the overall strength.
Yeah. Okay.
Yeah.
But the absolute strength, again, even if you scale it, is not exactly, it's not the whole issue, right? It is the robustness, the accuracy that you can maintain under these almost static isometric conditions. I don't know how to exactly estimate that, but that seems to be, for me, a more sort of task suitable metric.
Yeah, this is better seen in the other part, the part that we are working on, Dagmar, which I haven't presented. So maybe as a follow-up question, as a follow-up to your question, what we have been looking at most precisely was the positioning of the finger, because what I showed to you was essentially the position of the hand overall. But in the second part of the study, what we looked at was really how they placed the hand. And so, I'll just share that real quick. And so the positioning of the finger is absolutely key. And you know, the previous metric was probably not a good encapsulation of how they choose this posture of the arm, because this posture of the arm is probably related also to how they choose the position of the finger. So we looked at this more specifically. Okay. Basically, we redid the experiments by looking very carefully at the position of the finger, and we contrasted two things: when the watch is fixed versus the watch moving. So you have the watch here that can move, so you have more degrees of freedom to control for, and when it's fixed. And so with this, we were able to better understand how they choose to position the fingers in relation to the degrees of freedom to be controlled for. So when it's moving, when the watch is moving, in fact, what you observe is a typical type of distribution. Here is for screwdriving, which is the cell phone example that you mentioned before. One hand is supporting, let's say, the cell phone or the watch, and then the other one is doing the screwing. But when you have the watch is fixed, you cannot move it. You'll think, okay, well, they should just do it with, you know, the right hand or the left hand, and just do this, you know, screwing in with only one hand. But in fact, they don't do that. They use both hands. And this is where this analysis became quite interesting, is that there was a lot of variability in the positioning of the finger. And so if you compare, you have on the left-hand side the moving base condition when, okay, you have only this distinction. And then when the watch is not moving, then you have a distribution of posture between the two hands. And observe the way that they're using the finger. I mean, sometimes they use them to apply force vertically, sometimes to hold it and to the rotation, sometimes they do a combination of those two. And this, with the left hand and right hand, sometimes they have to coordinate the two hands to achieve the motion. And so you could also see how they are distributing this force and torque control between the two hands and with the positioning of the finger. But of course, it's there is a lot of analysis behind that, so I won't go into the detail. We're not yet at the stage of being able to determine why they choose this particular finger posture in terms of the force to be generated, because as you said, the force is very small. So it must be linked rather to how precisely they control for force in that posture. And I don't know, I would love to have some help from people who know more about this. Is there more noise in your perception of your posture and the force that you perceive at the finger depending on the hand configuration? Possibly. And this is something I would very much like to look at in the second stage, is to understand why certain posture are preferred, and also why certain configuration, let's look just at the right hand side, certain configuration leads to more success than others, even though all of this configuration in principle should be able to apply the correct motion and the correct force. But some are more successful than others, and I don't know why. So I have more questions than answers.
Question, if I may.
Sure.
So I had to step out, so you may have covered this and I missed it, but did you see any difference in the specialization of hand function between people who were left dominant or right dominant?
We had only right-handed people. In fact, there are very few people who are left-handed in fact, we had only one subject who was left-handed in the cohort, so it wasn't sufficient to do a statistics. In the cohort of the apprentice at watchmaking, and there we cannot control. So we can take possibly other subjects who would not be the watchmaker apprentices, and then get a better distribution of left-handers.
Do you have any idea if there's a sex difference?
Sadly, there again, gender distribution is poor. There was only one female. So we had her, but we could not do a statistics on this. Yeah.
When you're talking about like very small forces, what is the smallest force they have to accurately achieve to perform some of these things, and like what is the error that they can have in that force to achieve the task?
So the smallest force will be sometimes 10⁻² Newton for some of the watches, and I suspect that the precision is about 10% of that for some of the watches. Not the one that we're looking at, because this one is easier. This is the one for people who need to be trained. But at the end of their apprenticeship, they're working on very expensive watches that are actually even smaller in scale and made of gold. And there, this is about the level of measurement. So we don't quite know if they still sense it. We ask the teacher, do you feel when it gets in? And they say they do. But I don't know if they feel it or if they observe it visually and they have the impression of feeling it. I don't know. We don't have, even though we've really developed all this system to be able to measure precisely the tactile information and the force, our instruments are not precise enough to go to this level of the watch. So that's why we stayed also at the larger watch. And we stayed also at the level of the larger watch, because this is when the apprentices learn. Once they're good at that, they pass exams, then they can go to the other watches. And according to the teacher, they're hardly failing by that time. So we decided not even to try this.
So another question is, how important is the material of the peg?
It's a good question. So in watchmaking, one thing that they learn to do is to build their own tool. So they build also the screw. They mold it and they do all of that, and they have to learn to do it correctly. So clearly, the way that they build a tool is very important. We haven't studied that. These tools are always in similar material. Again, it's either gold or silver, or it's a simple metal as the one that we're looking at. They are usually fairly rigid. But they may break, and that's an issue. So the student get penalized if they break the screw or the tool, and they get penalized two ways. One, of course, grades, but the second is that they have to redo it, and then it takes another half a day or 2 days of rebuilding the tool. Strong penalty. So I guess your question is, will the posture of the hand change depending on the material? I don't know. It could. But the thing that we noticed is that the posture that the student adopts at the end is similar to that of the expert. So it's as if the expert have learned once for all what is the optimal way of holding tools. And we have really incredible videos of those experts coming and just screwing in all sorts of things in milliseconds. And always with this very particular posture on the tool. So maybe they've learned something that works for all watches. But I should be a little careful here, because we've looked only at experts who are the teacher in that school. We haven't gone to watchmakers, even though we could. In Switzerland, you have watchmakers that design single watch for one particular wealthy client. And in this case, they have to really do it very, very carefully. So it will be very interesting to see if they also search, these experts, do they search for different posture when they're creating a new watch, which is made of diamonds and which is made of those, because they have to be super careful and they're probably searching their way there. But to study that will be very complex.
Are these watches normally assembled by humans or by machines? And how far do you think we are from having a robot that could assemble a watch like that?
Yeah, you're working on a dangerous terrain. So the trademark of most of these watchmakers is to see that they're handmade. Mm-hmm. Okay, the reality is a little different. So a lot of it is still handmade because it's a trademark, not because it couldn't be replaced to some extent, sadly. But for the one-piece type of design, this is still handmade because it wouldn't make sense to try to have a machine to try to do that because the assembly is very complex. But for a lot of them, I think we're at the stage where it's possible to manufacture that. And here is one example of I don't know if you Swatch, if you know it. This is really almost completely automated. So there are parts that can be automated. It depends also on the size. It depends on the material. It depends on how expensive it is. It depends on how much they can afford to lose to have poor products.
So looking at the time, I think we should give a round of applause for Aude for a fascinating talk. And well, our usual action club continues because it's in the evening and nobody has anything better to do. But I think during daytime situation is a little different. So I would say we'll close here. If there are some urgent conversations, we can still leave the Zoom on, but let's do the official close here. Thank you very much one more time for a mammoth, fascinating talk in two different fields in a way. So, and bridging them beautifully. So thank you, Aude.
Thank you, Dharma. Thank you for the question. Okay, it was nice seeing you. So.